Hi, so I'm back with something. I haven't done anything in a long time. I've been busy with some kind of different things. So today I thought we were doing something kind of basic. We're just doing some kind of uh, traffic system, very basic from an EPS. Um, So the idea is to have some kind of simple background vehicles moving around and not intersecting on an environment, and doing it without having to go through a crowd sim or etc. So we're doing a very basic pop sim with some post work to make it look okay. So what I have right now is just an EPS that looks like crap, as they sometimes do. So first thing would be to settle this to get it to work. So I'm going to start with just making the EPS look decent. So I'm going to drop down the connectivity in order to get each line separately. So after we have the connectivity, we can drop down a for each node. So we can do a for each to connected, we get another connectivity, but we can remove that. The connectivity I'm going to change to primitive, and I'm just going to plug this in. And what we get then is a single pass for each of these lines. So when we have that, we could easily just start off with removing the geometry, because we have polygons right now that looks like crap. So we drop down on add node in order to do that. So just delete the geometry but keep the points. And the good thing is we get a decent order with these. So with that down, we could then do another add sub and just do a polyline from it. Let me see here if we do by group, we get this. So there we go. We have this road system. That is actually a small town here in Sweden called Landskrona for some reason. And I mean, these could be drawn by hand, of course, or it could just be something you import. There are a lot of resources for having these kind of things. I'm gonna drop down a transform in order to rotate it. So I'm just gonna rotate it to get it to lay down. So we do rotate minus 90 degrees. And there we have it on the ground. And I'm also going to transform this so we get it to a more reasonable scale. It doesn't really matter, but I think it might be a good idea. So I want this to be like 1 kilometer by 1 kilometer approximately. And right now it's rather a meter. So I'm just going to scale it up by 1,000. And what we get then is, make it like 1200 or something. What we have done is something by 1200 by 8056, which is good. Before we do that though, we could do a resample in order to get these more even out, because what we have here, if we look at this, we have the points not very good distributed. So I'm going to write down this, I'm just going to take it down to maybe something point 0.1 maybe, or even a third, or maybe 0.5, something like that. So we have an even distribution of points. So that's good. And what we can do now is, if we were to have a ground plane here, we could just ray it on, but since we don't really need to do it. So we can just skip that from now. And then we're going to run a polyframe. And I'm just going to plug in the computer tangent. So what the tangent is, it's basically, if we just plug it in as a normal instead, I would do tangent name n. Yeah, so we're just gonna visualize this, and we're just gonna scale up the normals in order to see it. So what we get from a tangent is this. We get something pointing towards the next line all the time, which is good. We can see that this movement is something we kind of want. We could see what happens if we put on a fuse before it. I don't think it will be that big of a difference. No. We have to bring it up quite a lot in order to, but we don't want that. So we just keep it as it is. We can skip the fuse. Good. So after we've done that, we could put down a volume rasterize. And in order to get this into a volume, and the reason we want that is because we want to affect our cars by this force rather than something else. And the reason for having a volume is that we can smooth it and we can get a better movement, I think. So what we're gonna do then is just drop down volume rasterize attributes, and we're just gonna rasterize the normal. And maybe we need to look at the particle scale here and the voxel size, because right now we get a few too many voxels. I think 28 million is kind of exaggerated. So I'm gonna bring up the voxel size to something like 1 maybe, and I'm gonna bring up the particle scale to something like 6 maybe. I think we have to try this, but I think that might be good. We could try a velocity blur, but then we have to rename it, so we don't care about that. So that's good. But in order to trail this or see what we actually have here, we kind of maybe should move on and also have our road, so to speak. So what we can do is we could take our sample here, or after the transform, we have this big thing. So we could drop down a sweep here, and what we could do is we could plug in a circle that we first of all get to have a polygon and bring it down to 4 divisions. We can just look at it, and what we would need to do is of course rotate it. So we could rotate it 45 degrees, and we get this, and we could then transform it and try to get something that's good here. So what basically we want is this is the outline of the road, so to speak. So we're just going to bring up the scale to 1.7, 0.1 maybe, and yeah, I think that's good. So we can plug it into the sweep. What we have now is this. It looks a bit too small, I think. So just gonna bring up the uniform scale here, see what happens. And you see this is not a perfect solution, of course, for many reasons. But it could work. Just gonna I don't know if is it. Do we need to reverse this? I think we do. So after the sweep, turn a reverse in order to flip the normals. And then we don't need a normal actually. So there we go, we have some kind of road system, which is good. And what we could do now is we could just do a point trail, a volume trail, in order to see what we have here. So we plugged in the volume in the second input, we choose normal here, and here we do a scatter. So if we look at the scatter, we can plug that in there, and we see something very tiny. So we can bring up the scatter points to maybe tenfold, and in the volume trail we could just make the length longer. So here we see something, we see some kind of vector field that gives us turnings, etc. What we want to do is we want to smooth this out, so we can do a VDB smooth here, and that gives us a smoother result. What we want to do is we're just going to bring this up quite a bit, I think. So let's bring this up to, we can use the mean value, but we can get it like 4 or something. I think that's good. So that's good. We have our sweep here, we have our road projection. What we also want to do is we want to have a road that this is too big, I think, maybe though, because we don't want them to overlap. So I'm going to bring this down to something like this. You could do a lot of operations to get this better, of course, but I mean, I think this is good enough what we're doing right now. So let's say that we're happy with this. We could then do another copy of this, because we want, because this will be a row that we actually use. So we can put down a null here, which we call out road. And then we also want, when we do our simulation, we want a road that we project our cars back on. So we're going to use a reverse here as well in order to get normals right, and then we're just going to do a little bit smaller here. So do something like this, I guess, like 1. and this is where the cars are allowed. 1.1, I don't know exactly. So that's good. What we could do then is we could take out the top here in order to scatter our cars. So what we're going to do is we're going to do a group, and we're going to group this by normals. We're going to have a straight upward normal, and we're going to bring down the spread angle a little bit, so we only have the top faces. And then we're going to do blast off everything but that group, and now we have the top here, which is good. And on this top then we could then scatter the cars. So we want to have this highlighted just to see how the distribution looks, and I think this is fine. The relaxed iterations we could bring up maybe a little bit. We don't, I think it's, no, maybe it's fine, they're not really intersecting. And let's say that we have 300 cars to start with or something, not 3000, rather 300. So that's good. We have our cars. So one thing to think about as well with the sweep here, right now it's not really a problem, but what could be needed if your terrain is, let's say that we have a terrain that's a little bit off here, if we were to ray this on into something that looks a little bit more bumpy, you would need to have an up vector here as well. So if you get a strange result from the sweep, that might be it, and then you just drop down a wrangle and give it a vector which is called up, and you say it's equal to 0, 1, 0. That just gives the sweep the knowledge of what's up. But right now we have flat terrain, so it doesn't really matter, but usually that's not the case. And we could just for fun do something else just to show you that maybe it's a little bit more interesting. So we're just gonna we drop down our grid here just to give us some kind of terrain here. So we drop down a grid, and we could probably do a match size here, I think. I don't know if we could. If we take this and plug it in and scale to fit, yeah, it works. Maybe it's uniform scale. No, we can't do that. So we can do like that. We can just bring it up here. Maybe 50 by something like that. 50 by 80. And if we drop down a mountain here, we don't get that much because it's a little bit too less of a height. Let's say that we have something like this. I don't know. Maybe element size could be smaller. It's very low res right now. I'm just gonna bring it up so we have something a little bit more. 160. Yeah, I think the mountain here is quite off. Bring up the element size. Here we go. Here we have something. Good. So if we were to take this and ray it on, so we drop down an array here in between. We can just do a minimum distance, I think. Points, minimum distance, and we have something look like this. And if we now were to skip this, we can see that some rays get fucked up. See here, we get these problems. So if we instead were to use this, kind of gets sloppy. We're just gonna move this down here. Do like this, do like this, do like this. Sorry, wrong button here. No, we don't want that. We could do A down here instead. Good. So if we were to add this one here instead, and plug this one into the sweep, we see that we get correct results, which is a good thing. So let's maybe keep it like that. What we probably should do though is that after the ray, we should put down, I could put that in as well. We should put down a resample again, because it might get a little bit uneven. So we're just going to do a resample here as well. And we could probably use, we have 005 there, so we could probably use like 5 here or something, I guess. Yeah, that's very similar. So that's good. And now we have these, and we have them reversed, and we have a scatter, and we have a volume trail, and we also have the out row that should come there. So good. Now that we have our cars, we could drop down a pop network, and we can just plug this in. And in a pop network, we then want all points. So instead of scattered surfaces, we can use all points. And we can go to birth and say that we only want them birthed on the first frame. So we just do $ff is equal to 0. Sorry. And we then want our volume, which is here, where we can drop down a null and just call it out vel, can we call it? But remember that this volume is called n. So if we do a pop advect volumes, we could step to this out vel, we could plug it in here, and we should use the field name of normal. And we also might want to give these a p-scale actually. So we have these, and just to see how big they are, we're going to drop down a copy to points, and we're just going to drop down a sphere to start with. And we can see that these are going to drop down a wrangle here in order to, or we could actually, no, we're going to drop down a wrangle here as well. I'm just going to see at p scale equals to 2 maybe. Let's see how that looks. Yeah, I think that's good. I think that's kind of what we want. If we have the road as well, that may be a little bit too big, maybe 1.6 maybe. Yeah, I think that's fine. So that's good. Now we have a p-scale on them as well. So we have our normals here and we advect them, but just take a look and see what's going on there. I think we should bring up the amplitude here as well, and maybe do air resistance as well. So I bring it up to 8 and maybe 5. Let's take a look what happens. So we have these moving. Cool. We should put on real time here. We can see that our car's moving. That's good. What we could do in order to just have something that we could just drop down. I have a just gonna. I have a car here, which is very basic. You can see a low poly car, and we could just take a sphere here. And what we could do is we could do match size, because this car is very big right now. So just going to do match size, and I can translate it and get the scale to fit. I can do uniform scale. So now we have something like this. We could drop down normals in order to clear this out, because I think this is made in another program, and I think it's made in like Cinema 4D or something. So that's good, and you can of course use a better model as well, a more high-risk model. I'm just going to probably reduce this as well down to 20%. I think that's fine. And now I'm going to use this instead for the copy to points. So you can see here we have something good, and we're just going to drop down from the PopNet instead. And what we have now are these cars that are very chaotically moving and turning around, which is cool, but not what we want. So first off, we're just going to drop down a transform here. And just rotate them correctly. And I guess we need minus 90 here or something, right? Yeah, that's good. And we're gonna see how they gonna do a merge here as well to see how they look with our road. Just do an object merge here because we have the road upstream. We can do out road, plug it in and see. So we have a bit of problems here, right? First off, we need to move this up, so we can do minus -in, and now they are actually on the road, but some are still chaotic. As you can see, they're kind of getting chaotic, but that's not a problem. So what we could do then is we could, of course, give all these cars an up vector as well. So we can take our old wrangle from up here. Let's copy it and paste it here. And that clears out some of the problems. They now are, but there are also some cars that have ended up below. So what we need to do now is we just need to ray the cars back on the road in order to have them actually not moving outwards. Just gonna see here how the trail looks. Yeah, we have this upwards and downwards, but yeah, it still doesn't really work. So let's do that. We have our road, and then we have our smaller road as well, which is this one. So we have this, which is the up part. So if we do a null here as well, we can call this out road projection or something. And then we can just drop in the popnet, do a subsolver. In here we could just drop down an object merge, bring up our outroad project. We can take these and we can just ray them on. So what we can do here is we can take the points, we can take a minimum distance, and we can just ray them on. So if we look at it now, we will have this, and if we combine it, we will have this. So now they're actually moving on the roads. But some cars get fucked up, definitely. And they have a little bit of a problem turning. So what we could do actually is just use the smaller ones here as well instead. Because right now, oh no, sorry. What we could do, just let's look here. Maybe if we bring up the voxel scale a little bit, we get a little bit smaller stuff. That might help a little bit. But what we also could do is that we could probably, let me see here. So what I think is that maybe we could, maybe doing a fuse, because we have some problems here, I think. And I think solving that might give us a little bit better results. So I'm going to do a fuse here. And I'm just going to bring this up quite a lot until we have a little bit of, let me see how this looks. I think this might be better actually. Gonna bring in some more points just to see. I think this might be better actually. So let's see how this looks. Still have a little bit problem turning. So I'm gonna see, we're gonna fix this. So I'm gonna bring down the height here a little bit, and maybe it was a bit too extreme, it's hard to tell, just to see if it works. So bring this down to 3. We have the ray on, we have the resample. What I think might be a problem is that, yeah, I think the resample is too low, and then we bring it down. Yeah, I think we're gonna put down resample here as well, and bring up the length to 1 maybe. Give us a bit more detail, and I think now we will see a smoother volume trail. Yeah, that looks a lot better. We still have some problem areas, but overall I think this will give us a little bit less of a problem. So go back and see how it looks now. Yeah, this looks a lot better. There's still a chaotic area here, but we will get rid of that in the post thing. Like I said, this is a background thing, so yeah, we're happy with this. This is good. So let's bring in a little bit of interaction between the cars. So what we're gonna do is we're gonna go to PopNet, and what we want is we want some kind of just a little bit of randomness. So it's gonna run on a pop force and give us a little bit of noise here. So maybe like 5 in amplitude, and we can just do a guide here. I think it might be a bit too gigantic, or a bit too low frequency. Yes, we can see swirl size. We can bring it up to 4 maybe. And I don't know if we can zero it out in the Y. Doesn't really matter. We still get it, yeah. What happens when we do that? No, it doesn't really matter. Never mind, we can have the Y thing. It will just be projected anyway, so it doesn't really matter. So that's good. We're gonna use crowd thing. That's what we're gonna remove it right here. We're gonna use a pop steer avoid. No, sorry, we're gonna use a pop steer separate, and just to get it to separate a little bit. So we're gonna remove the field of view, and we're gonna bring up the search radius to 20. I don't know how far we're gonna go here. Maybe go to 10 and 20. See what that gives us. And I mean, this will take a little bit of tweaking. We don't want it to be that noticeable. We just want them to break a little bit when they see each other. I think this is good. They're avoiding each other a little bit. If we bring this up to far, we can see if we get the problematic areas here. That seems to be going good. If we bring this up to like, we can use force separation here, and what we will see then is, maybe we'll see it. We can just look at the points instead, so it goes a lot faster. They could get really jumpy. I see it gets a little bit, so we don't want that. See, there should be some kind of interaction more. They seem to be doing okay even. I guess they're too separated in order to notice. If we were to bring up the P scale, we bring it up to like 5, 51. Okay, this is just crazy, of course. 51, we can bring up to 5, sorry. And yeah, now you'll see they get, this is not, they tend to do alright, but yeah, it gets really hard for them. So this is of course too high P scale, so we're going to bring it down to 1.6 again. And but when they are this separated, it seems to be doing okay. But you could use, as you see, it can work pretty well. They avoid each other a little bit, and that's cool. So we're also going to give them a little bit of random speed. So if we go into the PopNet again and go to pop at vec by volume, we can just do a vex expression. And what we could do is we can just do well scale, which if you hover over velocity here, you see that well scale is the parameter for that one. So we're going to do that multiplied equals to a fit 01. So we're just going to take a fit 01, which gives us refits a value between 0 and 1. And then we're going to do a random function where we use the ID. So this gives us a value between 0 and 1 based on the ID random. And we're going to refit that to 0.9 and maybe 0.1, 0.2. So that's good. And now we have a little bit of a randomness to the velocity scale, which is good. And seems like something went crazy here. Let me see here. Ah, you see 9, not 0.9. I thought it was off. So let's see now. We have a little bit of random speed to them, which is fun. And yeah, they're doing okay. Great. But we still have some problem areas, and we have some cars that just end up being fucked. Like up here, we see we have these ones. And often with these kind of things, it might be easier just to remove them. But we could, of course, remove them dynamically. So in order to do that, we're just going to collect some attributes, and we could either do a subsolver after we're done a popnet, or we can just do it in the popnet. It's either way. So what we want to do is we're just going to collect some data. So let's go into the popnet and do that. So we can drop down a pop wrangle. Pop wrangle. And we're going to plug it in. And what we're going to do here is we're just going to calculate some things. So before we move into this, we're just going to give them some values. So what we're going to give them is we're going to do a max speed. So we're going to do f at max speed is equal to a mean speed is rather, maybe we don't need max speed, we're going to mean speed equals to 0. And we're going to do, what else do we need? Yeah, we're going to do f at distance. And this is just, if we have 4 cars, they might get plugged into each other. So we're going to call this min distance, sorry. Min distance, we do that kind of, actually we're going to do min speed as well. Call it, name it like that. You could do, you know, naming whatever way you want. I'm kind of getting used to lower uppercase style. What is it called? I don't know. Pascal style? No, I have no idea what it's called. Never mind. Rename it. Name your variables however you like. So basically what we want to do is we want to see the minimum distance there are from another car. And if it's too low, we're going to remove those. So good. Now let's drop into the popnet. So what we can do here is very simple. We can just do an if statement. So if length from v at v, that is if the length of our velocity is bigger than mean speed, then we're going to say, oh sorry, if it's smaller than mean speed, and that's why we can't have a mean speed of 0, sorry. So if it's smaller than 0, we're going to say mean speed is equal to, we have to have an at there of course. So if it's smaller than mean speed is equal to the length of our velocity. So what we're going to do, can I write correctly here? So what we're going to do here is we're going to say that the mean speed to start off with is like 100 or something, 1000. And mean distance we should say is like 1000 as well. So we have a high number there. So to always overwrite it on the first frames. You could also do if frame is equal to 1, then mean speed is equal to length of velocity. Well, anyway, we're also going to check the distance to the near points. So what we're going to do is just going to do an int near pt. We do that as an array, and we're just going to do near points, which gives us an array of the points. So we're going to do geometry input 0, and we're going to do at position, and we're going to say look 10 away and just find 2 points. I think that's good. It's going to see bindings is input is myself. And then we can just do, we can just say that we want to look at the position of this, so we can do a vector and call it pos2, which is the position from the nearest point. And then we can look at that with a point function, and we can say 0. We want to look at that with p, and we want to look at near pt, and we want to look at the second one here because it finds itself first. So I think that's good, right? And then we can say distance. We can call this distance. We can just do float distance. Distance is equal to distance between our position 2 and our position of the point. And then we can do a similar if statement as we did up here. Just going to copy it and say if distance is less than min distance. Let's go see how I call it min distance. Yeah, I did. And then we just want to say that min distance is equal to distance. Let's see if this works. I'll go down here and see the geometry spreadsheet. See here, yeah. Min speed, yeah, there's a problem here, but you can see that they go down. If they find something, they go down and get smaller and smaller. So we can see that some of these have very small values. And this might not be as relevant now, but if we have more cars, that would be good. So we're just gonna see we did something wrong here. Min speed should be a capital S. So there we go. Oh, and we have the problem is that the first frame here we get 0 because they start with 0. So we're gonna say we can do activation here actually. I can just say $ff is greater than 1, and then we have min speed. So what we get then is when they actually stop, we will have that recorded. So if we look now, we have this and we have the merge here, but we can then drop down in this post solve thing. We can do if at min speed is less than threshold speed, and then we do remove point. And then we do the same thing with the distance. So what we can do then is we can bring up these, and if we look at the problem areas, let's see where they are up here. So we can say, okay, let me see here, min speed, they should be removed. Sorry, what's happening here? If min distance is less than threshold. Okay, let's see, maybe it's, there they are removed actually. Yeah, so we just bring this up, and then we get that back rid of those. And if we were to have, like, let's say that we have 1,000 cars instead, what we might have is too densely packed some places, and then we could just use this in order to get rid of, let's see here, if we get something packed tightly later on. Let's say that, okay, these two are too tight. Let's say that we think that we get rid of a lot of cars, of course, but then we can just say we can bring up this threshold, and then we get rid of those that are too densely packed. But of course we need to do something else as well here. Sorry, we need to look at this from the end frame. So what we're going to do here is we're just going to do a time shift. Because what you can see now is that they get removed when they get too close, and that's not what we want. We want them to be removed all the time. So we can do a time shift, and we can just say, no, what do we call fend? Sorry. So we have a time shift to our last frame here, and what we could do is just attribute copy, and we can plug this in, and we could copy min distance. We can copy min speed. So what we get now is something that checks if they ever get close enough. So even if we're frame 1, we could still get rid of those that gets too close later on. So if we remove this and just see here that we will have later on this car up here will get fucked. So if we then drag up the min speed, it gets removed from the start. So that's a good thing. And we could bring this up as well and get rid of cars that will get too close later on in the simulation. So that clears out the problematic cars. Good. And yeah, that's pretty much it. We have something that could work for background operations, background things, just like quite a lot of cars that don't intersect, that have a little bit of random velocity that moves along somewhat along our grid. And you could bring up the resolution in order to get it better, and you can of course use a better car model as well. So that's it, and thank you.